All right. Any questions? Let's focus on. Okay, so we talked about all this business with the going up, going down, flying over, and all this, and we talked about when you have an extension that is integral, it satisfies both going up and inc. So I'm gonna give a couple of applications of this. Another theorem that's also important. I'm gonna teach you how to count prime ideals here. We say ring community identity. We say chain of primes has length n. So I guess if we just have a single prime, we would call that length 0. This is the standard way to count in these chains. It's just what we've done. We start counting to 0. And so we find the so there's different notions of dimension that you might encounter. Krull dimension is probably, well, from my point of view, is sort of the most popular. If I say dimension, you can assume I'm talking about Krull dimension unless I tell you something else. Of R to the supremum over all lengths of chains of primes. And on. So you look at all possible chains of primes, get this big collection of how long they are, and then take the supremum over all that. Now, let me also throw in this, and we might talk about this later, but we're not doing it now. So you can say the Krull dimension of R is the supremum of this. So maybe that's a number, maybe it's infinity, right? And once you hit infinity, you might think, well, can you talk about the Krull dimension being countable or uncountable? And certainly you can, because I've sort of written this chain discretely, but of course you can talk about a larger countable chain of primes and things like this, right? And I'll give you kind of an example that goes beyond this. So let's look at some examples of this. The dimension of Z is one, right? Because in fact, I can tell you what any chain looks like. There's a lot of them, but they all, if you have a maximal chain, they all look like that. In fact, so if you have any principal ideal domain inside a field, it has to, it behaves just like Z does. You'll have 0 as the minimal prime, and then so non-zero prime is maximal. Example. If F is a field, then dimension of field. What can you say about the dimension of an Noetherian ring? Right, remember, in a Noetherian ring, all ideals are finitely generated. Equivalently, every chain of ideals. So what can you say about the dimension of an Noetherian ring? No, you can't. You can't, not necessarily, right? I mean, that's so evil, Professor, right? Certainly, if you have any, if R is Noetherian, and P0, P1, P2 is a chain of prime ideals, then this chain is finite. So in particular, you can never have an infinitely ascending chain of primes. But that does not mean that the dimension can't be infinite, right? What could happen in your worst nightmare?
Chains of arbitrarily long length.
That's right. You might have some chain of length 1, another of length 2, another of length 3, and so forth and so on. And the supreme might be infinite, even though you have no individual chain that is infinite. The supreme might be infinite. So here's another question. Get out your tools, your saws and hammers and whatnot. How would you build such a This is a brilliant example, and I'm not going to go through the details of it, but I hope convey an idea of why this is true. Start with the field. It ought to be this. By the way, is this ring Noetherian? No, it's not. Right, this is very non-Noetherian. The maximal ideal generated by all the variables is not finitely generated. So let me be clever. I'm going to yes. Okay, so the first thing I've done is I have re-indexed this for some reason. We put kind of a little 2 set, 3 set, 3 set. All right, this is isomorphic to my first ring, right? Because these are just both of these are countable sets of variables, right? Still not a theory, but I am going to make it my theory and follow these things. Let S. I'm going to take some particular prime ideals. Notice what I pulled out here. Each one of these little blobs is a prime ideal, right? Because x11 is prime, because if I mod out, I've got this ring, which is a domain. This bit is primes, because when I mod out, I've just got to kind of limit its domain and so forth and so on. So I'm pulling these out in bigger and bigger chunks, right? And I'm gonna let S. It's easier for me to do this. So S is the complement of this union of prime ideals, right? And what is true about the complement of a union of prime ideals? That set is multiplicatively closed and in fact it's saturated. Right? And what I'm going to do is I'm going to build this new ring. Let T be R localized at S. Now, when you localize, there's a correspondence theorem, right? The prime ideals of T are exactly equal to the prime ideals of R that miss S, right? So the prime ideals of T correspond to primes of R that miss S. So they've got an empty intersection with S. Equivalently, is contained in X11 or X21, X22 or Xn1, Xn2, Xnn or done. So they have to be contained in one of these ideals. Right? In this localization, these variables also remain prime as well. So let me give you stacks of prime ideals. In fact, let me say this generally. In T, we have for all n a stack of primes Xn1, Xn1, Xn2, Xn1, Xn2, Xn. We've got that for every n. And I guess this is a stack of length n minus 1. Right? So your supremum, so for all n, you've got something of length n minus 1. So the supremum over that set is infinity. So this ring here, when you localize this set, actually has infinite Krull dimension. The way that it's been clipped and pruned, I mean, seriously, I feel like I'm doing buildings and grounds and I'm trimming some trees here. The way this has been built, there's no infinitely long stack of prime ideals. However, you can have them as long as you want, supreme infinity. Can somebody explain why this ring is Noetherian? Because all prime ideals are finite. Yes, there's a little bit of devil in the details stuff yet to show that, but in fact, it turns out that every one of the prime ideals is either one of these or contained in it, right? By the correspondence theorem, these primes are all finitely generated, right? So if you've got all your primes finitely generated, of course, there's no upper bound on how big these finitely generated prime ideals are, but so that's kind of this is a wonderful example that shows that you can have an Noetherian ring that has infinite Krull dimension, right? You can never build the stacks infinitely high, but let me ask you a question here. Here's another one. And this is for the, yes.
So
Why does, the prime, all primes being finitely generated necessarily imply that, like, the chains have to be finite, chains of primes?
Well, that was an Oklahoma problem, actually. That if you have, that the ascending chain condition on ideals is equivalent to the ideals being finitely generated, right? And so, and the theorem is also equivalent. Kind of the bigger problem, I think, was that a ring is Noetherian if and only if all ascending chains of primes terminate. If and only if all all ideals are finitely generated, and this is the big one, if and only if all prime ideals are finitely generated. Here's another one, for those of you that, I mean, you guys have a feel for what it might be to have infinite Krull dimension, right? I mean, if you look at this original ring here, let's go back to this before we localize. Because the original ring wasn't Noetherian, was it? I mean, this ring wasn't Noetherian until we localized it. So if you look at this. I think that, I think we could all agree that this ring is not Noetherian and actually has infinite Krull dimension. There are many rings that are not Noetherian and have finite Krull dimension. Those are actually pretty easy to build, right? But this one, both, it's not Noetherian and it's got, and in fact, I can just very lazily write down an infinitely ascending chain primes.
On these chains, we can always add zero, so we're in a domain.
Yeah, yeah, that's right. Certainly, he's right. I could start at zero. How high can we stack the chains? Well, there's infinitely long. So, what about the Krull dimension? I mean, so this Krull dimension is certainly infinite, but countably, uncountably. How do you know?
Well, because I've seen you prove it.
Okay. Anybody else see me through it before? Poor Grant. Let's give him a sleeping pill for a moment. This is actually, I can actually give an uncountable chain. Anybody know how to do it? I have a very poor choice of indexing things right now. Instead of indexing these by the natural numbers, I'm going to index these by the positive rationals. Everybody okay with that? Of course, these should be isomorphic rings. And the reason, because these are actually polynomial rings. So there's a bijection, a set bijection from the positive rationals to natural numbers, right? Use that set bijection to induce an isomorphism here. So these rings are the same essentially. They're indexed conveniently. Can anybody use this to write down a very large chain of primes?
Extra primes, right? The real positive.
Right. Let beta be any positive real number, and I do need a real number, not a fraction. So let piece of beta, the ideal generated by x to the gamma, or gamma less than beta.
Dedekind cut.
What's that?
It's like a Dedekind cut.
That's exactly what it is. That's exactly right. So notice that, for all beta, so if because you've actually got more variables in the larger one. If I agree with that. So this collection here is actually an uncountable chain of primes. Right? So that's kind of surprising, isn't it? Right? That this thing right here, I mean, for example, if you take a small field, like for example, F2, this is a countable ring. However, you get an uncountable chain of prime ideals, a strictly descending uncountable chain of prime ideals. Right, so there you go. So Krull dimension can be a little bit subtle here.
Can it get more uncountable?
Yes, you can actually, and in fact, yeah, it gets worse. I'm so glad you asked. Let B be a one-dimensional, say non-discrete valuation. And we'll set the value through. I think this may work more generally, but I know I'm good at value through, so all right. So we did a construction like this earlier, so a typical so in V, the elements look like either zero, you've got zero, or you have, let's say, x to the alpha u, or alpha and r. So I built constructions with these valuation domains. Remember how I used group rings? V equals, let's say F2, it doesn't matter, I can use any field X. So remember how I built polynomials out of this. Polynomials I use loosely because the exponents can come out of the positive rational or positive reals, and then I localize. And it turns out in this valuation domain, you got two kinds of elements. You got x to the alpha times a unit, right? If alpha is zero, is an like unit or zero, right? So in a certain sense, this is very close to being a PID, but the maximal ideal is wildly not finite generated, because no matter what you think the finite generators are, all you have to do is cut alpha in two, and it's there. If you look at Bx, this has finite dimension. Actually, let me, so since I used X up there, if I look at a polynomial ring in the variable t, this has finite dimension. And I think it's 2, but it's no more than 40. Right, it's no, so it's very tiny. If you look at B power, all right, if P inside Q are primes, B power T. So if you have two primes that you find in there, and you can compare them, then one of two things is true. One, P inside Q are adjacent. So there's nothing between them, right? They're as close together as you can get. Or two, there exists uncountably many uns. So in a certain sense, in this ring, every chain is bad, right? And I think that also if you take its power series ring, you make it worse, right? But of course, all you'd have to do to build anything is bad if you want. So suppose you wanted some cardinal and you wanted the Krull to be at least that, then take a set of variables that big and join it to a ring. And then you've got at least that as the Krull dimension. And in fact, as we saw from the previous example, probably worse. Okay. Other questions?
So actually, if you had two that are adjacent, and then a third that was adjacent to one of the two, then between the first and the last, there would still be a common.
Well, if you have two that are adjacent, that's one thing that could happen, but suppose you have two adjacent, there's no guarantee that you have something adjacent to either P or Q, other than each other, right? So actually, you can use your little observation to glean some stuff that's true about that ring. Right. So let me give you a couple of lemmas. Now that we've done some exciting examples. If R inside T going up, so if you have R inside T going up, then the Krull dimension of the bottom ring is no bigger than the Krull dimension. So let's see why that's true. Suppose. So basically what I want to do is I want to show that if I can build any stack of prime ideals at the R level, then I can build one that's at least that long at the T level. So every chain of primes I could ever find below, there's one that's of length at least that long upstairs. Suppose that P0, P1, Pn is a chain of primes in R. Now, here's how the going up works. P0 and P1 in R level. Now, going up implies lying over. So at the T level, the straight line means that when I take Q0 and I intersect with R, I get this. So I know that going up implies lying over. Now, because of going up, I can build Q1 that lies over this. All right. Well, now I've got Q1 over this, and I've got P1. So going up allows me to build Q2, and then I can go all the way up to Qn. So given any chain that I've got here, there's a copy of it up here. And Who knows, there may be more here, there may be some more in between, who knows, right? So. Going up allows construction of chain above P0. So dimension of T is greater than dimension of R. Because any chain here has got a chain of at least that one. Right, okay. And now, what comes next? Let's make sure I remember. Yes.
So we've written this in terms of finite chain, it's also written for an arbitrary chain.
Yeah, for an arbitrary chain, that this should work as well, because. Yeah, because what you can do, I think, is speak this in one bit at a time. So if you've got an arbitrary chain, then given any prime ideal down here, given any two prime ideals down here, you can get two up here by going up. And so you could construct like a one-to-one function from the chain down here up into the chain up here. Yeah, that's a good question, but I think you could do that as well. Yeah. There's a similar thing here, as you might expect, for ink lemma. If R inside T satisfies ink, then the dimension of the big ring is now less than or equal to the dimension of the small ring. So proof here. What does it mean to be ink? It means that no two primes at the T level that intersect in the same place in R are comparable. So in particular, let's start here. The chain primes. So we start with a chain of primes in T, and I want to be able to build a chain of primes that it's at least that long down at the R level. Notice that Q0 intersect R inside Q1 intersect R. This is a chain of primes in R, right? Now, notice that just in the blind, I know that if Q0 is contained in Q1, then this intersection is contained in here. And the strictness might go away, but it actually doesn't. In fact, we get all these are strict. And the reason is, note, if Qi intersect R is equal to Q I plus 1 intersect R, then Qi and QI plus one can't be comparable. So all containers must be strict. Because again, if, for example, if these two are equal, that means these two comparable primes collapse to the same prime, which can't happen. So there you go. So here is a theorem. If one inside P satisfies going up in ink, then dimension of all is equal to dimension. Because going up gets one inequality and ink gets the other. Right? So corollary. If R inside T is integral, then R is equal to M. Because we've already shown that an integral extension is both going up and in. So any integral extension actually satisfies the Krull dimensions of the same, which is enormously useful, right? So for example, let R be a PID, not, you know, well, actually, you know what, heck that, any PID, and of course you put that. Let K bar be the algebraic closure. I should say an algebraic closure, but whatever. If R bar is the integral closure of R and K bar, and this is sometimes called the ring of all integers. This set of Z and K bar such that Z is integral over R, then so in particular, the ring of all algebraic vectors, the set of all complex numbers that's the root of some monic polynomial coefficients of Z, automatically dimension one. Right? So right. Yeah. Okay. So in particular, and by the way, we also know, just for fun, since ours is PID, it's a proof of domain. This is an algebraic extension of K. So R bar is a one-dimensional proof of domain. Nothing else I know that. And proof of domains, by the way, exist in any Krull dimension you want, because you can build valuation domains, in fact, in any Krull dimension. Okay. Questions? Okay, so since we're talking about dimension, which is, we're gonna, a lot of the stuff, this has an important consequence in algebraic number theory. Let me give you kind of another one. So as a consequence, if R is the ring of integers of any finite extension rationals, then R is one. So it's very much like the integers in the fact that all the prime ideals that are non-zero are maximal. Because these things again are built this way. Take some finite extension, and then you take R, which is the integral closure of Z and F. This field is the quotient field of this. This extension is finite. In particular, since it's finite extension, this is algebraic over here, and so this extension is integral, and so it's a dimension one, just like you see this. Okay, so I'm gonna actually throw something else in, fun. We'll start on this today. I don't know if I can get through it quite today, but. One of the big theorems, I think, I mean, really a central theorem that can be involved is the Hilbert basis theorem that says if you have a ring necessarily with identity, if it's Noetherian, then its polynomial ring is Noetherian. And this allows, Noetherian is a very kind of finiteness property. It passes on up into polynomial rings. So by induction, it passes on to any polynomial ring in a finite number of variables. And this is why theorems in algebraic geometry work, things like this is very important. There's also another very important theorem about Krull dimension. Suppose R is a ring, and the Krull dimension of R is equal to n. This theorem is really a most important for finite dimensional. You'll see why. So suppose that you've got Krull dimension n. That means that somewhere in that ring there's a stack of primes that are n high, and no more than that. What about this? I could make this. Let me make this a little. I'm going to make this a little bit better in a moment. But can anybody give me a lower bound? So the dimension. So I can stack it n high in the coefficient ring.
N plus one.
N plus one. Okay. Do you know how to do it?
Sort of, start with your primes and R,
Yeah.
and then look at the polynomial rings that will extend them to Rx, so the stuff they generate in Rx. And then at the end, you've got one more, that's,
Plus
Yeah.
X.
There you go. Okay. That great. I like your all's answer. So suppose you have this. Suppose you've got this stack at the R level, right? How can I make one that's a little bit longer, T level? Well, the naive thing to do, and here this is at the level of Rx. One thing I can do is I can extend all these primes. notice this really is a jump, right? Because there's, by hypothesis, there's stuff in P one that's not in P zero, so that has to persist here as well, and so forth. And you just kind of do this, tell you this. And we'll talk in a moment why these in fact are primes, but many of you probably already see it. And then go a little bit bigger on the last one. Right, because this prime ideal has X in it and this one does not. Right, these are all prime ideals, and so it looks like if I've got something in long, I can make it at least one longer. And by the way, in general, I don't expect it to be any of this, because I can tell you right off the bat, if you have a field, right, then this Krull dimension is 0. And if you look at Fx, its polynomial range, it's a PID through Krull dimensions 1. So, you know, I'm n plus 1 certainly going to happen where that's, in fact, for a field that is it. Anybody give me an upper bound?
2n plus 1.
How'd you know that?
I've read it.
Okay.
I don't remember how to pretty well.
Right, I mean, this is surprising, isn't it, right? It turns out, and we will prove this, I'll give a couple of preparation times, but no more than essentially double the size. You know, double seems kind of arbitrary, right? But it's no worse than that. And they have actually, in the literature, it's been shown that this upper bound can be attained for any as a matter of fact, right? And in fact, the upper bound also works for a field, right? Because if the dimension of R is 0, then both of these are 0, and so it has to be 1, no matter what, right? So, let me start with a couple of lemata here. My first lemma, my first trick, note if P and R is prime, then Px comma X are primes. Okay, this is just kind of for me to complete my thought here. Proof. What this is this is I like to think of this as polynomials with a restriction that the constant term comes from the prime ideal P. And these are polynomials, all of whose terms are in the ideal P. Note that if you have the homomorphism R of X to R given by, let's not do that. Notice R mod P is a domain because P is a prime ideal of R. Phi of F of X is, yeah, so let me write down a form for this. A0 bar plus A1 bar X plus AK bar XK, where A bar is this cosine here. So you just basically reduce all the coefficients on P, right? This is a homomorphism. This is surjective homomorphism. It's pretty easy to see that everything's got a pull back here, right? This is surjective homomorphism, and the kernel And what is the kernel of this?
PX, so.
Right. Because how do you get to the zero element? You just have to have everything here. So PX is prime. Oh, actually, no, the kernel is. I meant to say PX. There, the kernel is PX. And here, if you look at pitchfork from RX to R mod P, given by pitchfork of A0 plus A1X plus AKXK is A0 bar. Here, this is clearly surjective. This is even more clearly the other one. With kernel of pitchfork equal to, well, what do you have to, what does it take to go to zero? Well, P and X, right? Anything in the ideal generated by X goes to zero because you basically nuked all the X stuff. And so to go here, you have to, the A0 just has to be. So this is prime as well, because the quotient is a domain. And so that's the first one, that if P is prime, then PX and P comma X. We'll move on with this next time. Any questions? Well, you have a good weekend. Oh, I forgot to mention, Keisha Cook is giving a talk today on presenting a scientific paper.